In this lesson, we are going to talk about features of exponential functions. Exponential functions are either growing or decaying. Some real-world examples are going to be in terms of growth, bacteria multiplying over time, cancer cells, damaged area in forest fires, water plants, Ebola, COVID, mold, things that just grow really fast. Decay is eating half of the same candy bar each day, radioactive decay, value of a car, treatment of diseases, or healing of wounds. You could Google a whole lot more, but we need to understand the difference between growth and decay. So growth is going to go up as you increase the x value. Decay is going to go down. The standard form of an exponential function is a times b to the x. A is going to be your constant, and as we learned in Unit 1, a is also your y-intercept, or your initial value. So let's make note of that. It's your initial value, which is also your y-intercept. B is your base. B is the rate at which you're increasing. As b gets bigger, you're increasing faster. And then x is your exponent. That's the key for exponential functions, is that your variable is an exponent. The parent function of an exponential function is y, or f of x, equals 2 to the x. And in this case, a is 1. So you can see in the parent function, the y-intercept is 1. Let's go ahead and talk about parts. We kind of mentioned this before, but in an exponential function, a is going to represent the y-intercept. So in a y-intercept, x is always going to be 0, and a is your y-intercept, the y value specifically. If you just have one number to the x, you can assume that a is 1. The b value, so the number raised to the variable x, is going to be how you determine if it's growing or decaying. If b is greater than 1, okay, b cannot equal 1, but if b is greater than 1, we have growth. If b is greater than 0 and less than 1, so b always has to be greater than 0. If b is between 0 and 1, so it's a fraction or a decimal that's less than 1, but greater than 0, that is where we're going to have decay. So for instance, our parent function 2 to the x is a growth function. As our x values down here are increasing, our y values are also increasing. This one, b, is 1/2, which is between 0 and 1. So as our x values are increasing, you can see that the y values are decreasing. We also have a new word called asymptotes. An asymptote is an invisible line. A graph approaches but never touches. This is specific to exponential functions. The asymptote for the parent function is y equals 0. So it's going to be the x-axis. A transformation, for instance, if we take a look at our parent function, okay, our asymptote here is y equals 0. But if we were to move the entire function up 3, that asymptote is going to be at y equals 3. So the asymptote is always going to be a horizontal line, y equals. It depends on how much you're moving it up or down. And then, of course, if you're moving it down 3, your asymptote will be at -3. The last thing we're going to talk about is domain and range. So again, we have our horizontal asymptote for this is a decay function. Why? Because a is less than 1. As you can see, it's going down and to the right. So our domain is all x values. We have arrow and arrow. So that means our domain is all real numbers, or negative infinity to positive infinity. Our range, however, will stop at our asymptote. Whatever that y value is, which is range is y values, it's going to always be lower bounded if a is greater than 1, and it will go to infinity. If a is less than 1, it will be upper bounded and go to negative infinity. So this is a decay factor. If we have a growth factor, again, our range here is still 0, okay, because it approaches 0, but it does not touch, and then it goes on to infinity, and then our domain is all real numbers. Let's do a couple examples. We're going to take a look at this. This first problem is going down. So as we're moving towards the positive x values, our function is going down. So this is a decay function. This is, you can see kind of where it flattens out, which would be at y equals 3. So therefore, my domain is always all real numbers. My range cannot go lower than negative 3, and then it's going up towards positive infinity. This is another decay function. My asymptote, you can see it kind of flattens out here at y equals negative 6. Domain, negative to positive infinity, and my range will be no lower than negative 6 and still go to positive infinity. Number 5, as we move towards the positive x values, we're going up. So this is a growth function. My asymptote is going to be at y equals negative 1. Domain, always negative to positive infinity. And my range is going to be negative 1 is the lowest value up to positive infinity. Now, what if they do not give you a graph? You can always use your graphing calculator to graph. However, we can determine these answers from just the equation. So my b value, b here, is 0.75. 0.75 is not greater than 1. It's between 0 and 1. So this is a decay. Oops. This is a decay. My domain is always going to be negative to positive infinity. For my range, I want to take a look. We're going to go ahead and graph this one. So this is 3. I'll put in parentheses 0.75x and graph that. You can kind of see it's bottoming out right at 0. So range is going to be from 0 to infinity. We could have known it was 0 to infinity because we're not adding something at the end or subtracting something. If you want to graph it just to be sure, that's always smart. To name 2 points on the graph, you can, when you type this equation into y equals, you can hit your second graph button. You've got 0, 3, and 1, 2.25. So those are easy points. Our y-intercept, remember our y-intercept is our a value. So our a value here is 3. So our y-intercept would be at 0, 3. And again, the asymptote is y equals 0 because I'm not adding or subtracting anything to the end. So that does not move my y asymptote or my asymptote. So my asymptote stays at y equals 0.